Good afternoon, everyone. I'm Manish, Karir, currently with the Department of Homeland Security Cybersecurity Division. The work I'll be talking about today was done while I was at Merit. So the collaborators on this project were with the University of Michigan and other folks at Merit. What I'll be talking about is understanding IPv6 Internet background radiation. And I'll describe a few interesting things that we've done in this regard. At a very high level, why did we want to do this? Well, we've done a lot of darknet study in IPv4. For example, we've been announcing one large darknet over 10, 15 years, and we've collected lots of data, lots of analysis, lots of experience in the value we get from that. And I think 40 of the last /8s that were allocated by the RIRs, we did a darknet announcement of those for a week at a time or more, just to try to understand the health of the network and how usable or polluted those network entities were. And that proved to be very useful as well. Some of you who are frequent NANOG attendees might remember the work we've done on the 1/8, the 5/8, and so on. All of them leading to some very interesting results of the kind of junk you pick up when you look at unused address space. And the idea there is really, the reason we're doing this is especially if we start in IPv6, we were hoping that if we can pick up issues early on, we can help improve IPv6 deployment as it gets started. So that was where we were coming at from this problem. Quick background for those who are not familiar with our work in the past. What are network telescopes? Network telescope is essentially announcing unused address space, picking up junk that gets sent to it, misdirected to it, and then doing analysis on what it is and slicing and dicing the data in different ways. The kinds of data patterns we pick up are worm propagation, especially things like configured. They pick a random destination address, try to connect to it. We pick up DDoS backscatter. We get lots of SYNAC from DDoS victims because of spoof source IP addresses. We will pick up lots of random scanning activity, like on port 22. And more interestingly, and this is what we found when we were doing the analysis of the IPv4 /8 darknets, we end up with a lot of misconfiguration stuff. We end up with misrouted syslog. We end up with video streams. For some strange reason, people are sending video streams to unused address space. Essentially, people have done something wrong in their configuration or in their network, and you can get a lot of value by identifying these issues and then telling people about them so they can fix them. So that's where we're coming from. What am I going to talk about today? I'm going to talk about the large study of IPv6 unreachable address space that we did. It covered about 86% of all allocated address blocks in IPv6. Next, I'll characterize some of this. What are the patterns? What are the trends we're seeing? What are we not seeing? And then towards the end, I'll talk a little bit more about what we did different in this study and some of the implications of that. In particular, the covering prefix methodology that we used in this study. So some of the previous work that has happened in IPv6, there were at least two other experiments that had been done in this area. One was a small experiment that announced a /48. And they just saw 12 packets in 15 months. Essentially, it's a small space. There's not a whole lot going on in IPv6. Then there was one large study by Jeff Houston over at APNIC, where they announced the covering /12 from APNIC for a period of a year and analyzed the background radiation that they saw there. We thought that was a great idea, so what we did was we then extended that same idea to all IRRs. We went to the RIRs, we said, can we do the same experiment that APNIC is doing for your address space, and we'll report the results that we get back to the community. And that's why I'm here today. So we announced 5 /12s, one from each of the RIRs. We got letters of authorization to do the announcements. We send them to our upstreams. The upstreams say, no way. And then we say, no, this really is signed. It's a real letter. And then finally, those announcements were accepted. We advertised these /12 prefixes via Merit's ASN. So we ended up with two data sets. One is a 24-hour data set. It's just one day of darknets. It's all 5 /12s. And then the next data set that I'll be talking about in detail is a 3-month data set. And in this case, what's happened is we've reduced the ripe /12 into two chunks, the /14 and the /13, and I'll talk a little bit about the reasons for doing that. And we'll talk about the analysis of those two different data sets. So, quick overview about what it is, what address space are we actually looking at? What traffic are we picking up? You can talk about random IP addresses that you see. They fall into 4 different categories: routed allocated, routed unallocated, unrouted allocated, and unrouted unallocated. Now, traditional darknets have looked at unrouted unallocated address space. This is address space where there was no other announcement in the network, and you just pick up, you just set up your announcement to pick up that unused address, unallocated, unrouted address block. So in the first part of the talk, I'm just going to focus on results for that traditional description. I'm going to talk about the differences we see between the different RIRs, the different trends, and differences between IPv4, comparing IPv4 darknet to an IPv6 darknet traffic, and also whether we see anything interesting at all. So here's the data set over time. What you're seeing is different RIRs that have different colored lines on the chart, and you're seeing about 25 packets per second from the ARIN region, and all the other regions have much lower traffic volumes. And in a lot of these cases, why this is happening, why is the traffic variation, boils down to the next few charts, which I'm going to talk about. Spatial analysis. We're looking at where is this traffic coming from, and destinations, where was it destined to. The red and the black lines are for APNIC and ARIN region specifically. So if you're looking at just the sources chart, what we're seeing is very few sources, almost less than 1,000 unique sources are accounting for over 90% of the traffic for the 3-month data set. Now that tells you that there's some very specific event there that can be tracked down and perhaps mitigated. In terms of destinations, it's even more dramatic. For the ARIN region, we see less than 100 destinations. So this data is going towards specific IP addresses, and specifically less than 100 of those account for 90% of the traffic. And for the other two regions, we see much lower traffic volumes. How does this compare with what we see in IPv4? Well, first of all, there's a clear difference in volume of traffic. Just like IPv4 and IPv6 traffic, there's a clear volume difference in terms of how much darknet traffic you see in an IPv4 darknet. For an equivalent for a /8 darknet in IPv4, you would expect to see close to 10,000 packets per second or more. In IPv6, we're seeing about, for the most amount, aggregated traffic, we're seeing about 25 packets per second. What is the difference in terms of the spatial distribution of sources and destinations in IPv4 and IPv6? Is one more dense than the other? If you're looking at just the sources, for example, we see that IPv6 sources are much more concentrated. IPv4 darknet sources have much larger variation. So in other words, pollution traffic in IPv4 is coming from a broader set of actors than in IPv6. In IPv6, we are seeing a very small set of actors and a very small specific set of data, unlike IPv4 where it's much broader. If we look at the types of traffic that we're getting in terms of protocols or TCP flags, you'll see in IPv4 the bulk of what we get is TCP traffic. And the bulk of what we see in IPv4, as I talked about earlier, is configure scans, is SSH scans, so all TCP events. We see some UDP events, but very little ICMP. Now what we're seeing in IPv6 darknet traffic, and remember this is the unallocated, unrouted darknet traffic, we're seeing lots of ICMP probing, and not much else, Not very little activity going on, very few systems right now in IPv6, so very few pollution traffic. This is why it was useful to do this study early on. So we said, well, one of the things that contributes largely to darknet traffic in IPv4 is probing and scanning activities. Do we see any sign of that happening in IPv6? So we went ahead and tried to do an analysis of the data, and what we find is there's no real evidence of broad, large-scale scanning. We do find some regional, local scanning attempts. There's nothing to indicate that those are malicious. They're perhaps attempts to map out small sections of the space, perhaps misguided or misdirected attempts to scan traffic. One interesting thing that we do see is we see leak of linked local addresses. So FE80/10 are linked local addresses, and they should not be routed and should not be made available to anybody on the internet. But as it turns out, people are not blocking those at the routers, and they do leak out into the public internet. There were only a few set of sources that were generating this traffic, but they did account for a very large number of packets within this data set. Worm activity. We looked for, we had no reason to believe that we might see it, but we said we should look just in case there is something going on, and as it turns out, there's no worm activity that we could spot from darknet traffic in IPv6. So now let's talk about what we did different in IPv6 for this experiment that we haven't done before in the IPv4. Remember, in the IPv4, we were largely announcing unallocated, unrouted outer space. In this experiment, what we did different was, in order to maximize our coverage area, we used a pull-up route. Pull-up route essentially takes the traffic that was unclaimed by a routing table and says, here you go, this is the unclaimed traffic on the internet. Now, that has some implications, and what is interesting to see is this was one of the unexpected side effects of our study is we're able to find that 95% of the packets we now observe are not the traditional darknet. They're different. They're something else. They're pointing to routing instability, and they're pointing to apparent leakage of internal address space. So let's go through a quick reminder of what the different words are, right? So one is routed, allocated. That means it was allocated address space and it was routed. We should not have received a packet for this space, but we did. This was unexpected. Unrouted, unallocated. This is, unrouted and allocated. This is address space that was allocated to an organization, but it did not have an entry in the routing table. Also strange. Why were we receiving these packets? So let's talk about what these packets are and where they're coming from. So let's talk about, in particular, the allocated and the routed data set. We see 36% of our packets, of the total number of packets we received from our experiment, fell into this category. These prefixes were largely coming to us, we assume, from routing problems, instability, perhaps very, very small outages. We are not able to confirm for sure that these were micro outages, but we have some interesting indicators. So we went ahead and did a separate study just looking at route views data to see, well, what is the stability of an average IPv6 prefix, and is it different from an IPv4 prefix? And as it turns out, yes, IPv6 prefixes in general are less stable. They are also less well connected than an average IPv4 prefix, and they're originated by, in general, coming from the edges. So overall, what we are able to confirm is that an average IPv6 prefix does have less stability than IPv4, and that potentially is a contributor to us picking up a fair amount of traffic of this type. Now, if you look at the allocated and the unrouted traffic, these are once again packets that should not have been leaking out. Potentially, this accounts for about 59% of the total number of packets that we observe in our data set. 86,000 unique destinations are targeted due to this, and potentially this is because of leakage of internal address space. This should not be happening, but it is. We were able to identify actually two specific contributors to this traffic. One was a large wireless service provider. We contacted them, and they said, no, this couldn't be happening. We use this internally. And like, no, this really is leaking out. And we share with them the data, and they're like, oh, well, thank you. We'll fix it. We did the same thing with another hosting company that was the second largest contributor, and both operators were happy to have identified the problem and fixed their misconfiguration. So that was a good, happy ending to that analysis. Unallocated and routed traffic, this was just strange. It's not allocated by an IR. Why is there traffic for in the IPv6 Internet? Turns out it's just a small fraction of it, but we do see some traffic, and most of it we identified was due to some experimental scanning that was just not being very careful to not scan unallocated space. So we contacted the three organizations, and they said, yep, we can do this better, and they did go ahead and make those changes as well. So long story short, what did we learn from this? Well, one of the things we learned is there is a distinct difference in IPv6 darknets. We also learned that there's value in doing the study which can have an operational impact. Feeding this back to the organizations, where the organizations are able to remedy some of the situations, is very helpful. And I think getting a head start on this in IPv6, as we did, hopefully will lead to fewer problems in the future. This also leads to a second follow-on research that we would want to do, is looking at routing stability for IPv6. We did not expect to see the level of instability that we did, but obviously there are some fundamental issues there, and we would want to study those in a little bit more detail. The covering prefix methodology that we used in this study is itself interesting. It has some different implications than a pure darknet study. So, long story short, we did a large study of unused address space, unreachable address space in IPv6. We were able to characterize typical background radiation and the trends and how it compares with IPv4. Some interesting case studies. For example, we found NTP traffic that was being misrouted, and there was some BGP session connection attempts as well. And we spent a significant amount of time then looking into the covering prefix methodology, which gives us something slightly different, and we were able to identify things like routing instability, leakage of address space as well, which were unexpected results and unintentional results. Questions? Lots of time.
You need to unmute the question mics, please.
I'm a little short. Heather Schiller, Google Fiber. You should have titled your presentation, How to Hijack the V6 Internet with Everybody Watching. So just because you got LOAs to route the prefixes doesn't make it right. That is not darknet space. It's actively allocated to real companies who are doing business and actually pushing real traffic over it. And I think that it's unethical to have routed the /12 prefix. It's not that different than what some Russian companies who are announcing v4/8s are doing. And when a network goes down or something becomes unstable, you're getting traffic that you shouldn't be seeing. And I think that we should be able to have more trust in the routing system and from, research organizations to do responsible research. I don't think that this is right. And we've taken it up with the RIRs about why they permitted this prefix to be allocated. If you want to do darknet research, that's fine, but announce prefixes that aren't actively allocated to organizations already.
I think that you make a good point, and I agree with you that there were some unintentional outcomes. That's not what we started out to do. Our expectation was there would be nothing else here, and we would be fine. Now, as it turns out, this also brings up an interesting question, and I'm glad that this question is something that can be discussed here, which is there's potentially other people who could be doing this, right? And have we done something useful by at least highlighting the importance of you yourself being able to do this? To understand potential leakages and potential routing instability in your prefixes. And in the organizations that we work with, that we were able to identify, they were happy that we did do this experiment and were able to help fix some issues that they weren't aware of. So perhaps I think it talks to the importance of being more aware and perhaps doing this more by the organizations themselves and not by us.
So if you're announcing your own, you're talking about organizations that were not announcing their entire prefix, and you saw leakage for the pieces that they were using but were not announcing.
So let me talk about this in a slightly different way. There's an entirely different experiment that we constructed by injecting an organization's prefix from multiple different locations, the same prefix with different lengths, and then doing a fire drill. What happens if there's a route hijack of my prefix, and I'm going to try to inject this, at some regular interval to see what happens. I mean, we have to have an understanding of I mean, organizations probably, so for example, network penetration testing is often done to try to proactively identify issues that might happen and things that might go wrong. And perhaps this is something that...
Sure, but with the organization's permission.
Yes.
You did not go seek the permission of the organizations that already had allocations in this NetBlock before you did this work.
That is correct. And that's what I'm trying to point out is if this were to happen in the future, that would be the version. The reason this happened this way was because we were not expecting this to happen.
Someone else, because like, how could you not expect to get trapped? Like, V6 not that different from V4. Like, this happens in V4 as well. Like, I just can't wrap my head around why it was okay to do this in V6. Like, if you did this in V4, people would lose their minds. And, like, you'd be all over the news and Renesys and BGPmon and all of this stuff. But, like, because you did it in V6 and no one's paying attention, it's okay? I don't agree with that.
I think our intention was to identify issues and to highlight them in a public forum, right? And that's why we're here reporting our results, right?
Totally missing I'm talking about, like, how ethical is it to hijack address space that's in use and allocated to other people without their permission?
But this was not. But this was not a hijack.
Results,
so the traffic was not hijacked. The traffic that was collected was unclaimed, unrouted.
But that's absolutely not the case, because it is not the case, because you had announced the entire /12, and so there are pieces of that are allocated to our organization. And so if something happened where some route went away or we misconfigured something, it is hijacked because now you're getting that traffic,
so,
rather than it not having a route and not going
So we did not expect that those incidents were actually taking place. We thought the the routing system is stable and that there will be nothing coming to us that shouldn't be coming to us.
I'm sorry, but I call bullshit on that, because you know how it works. It works the same way in V4. And you intentionally went looking for it without notifying operators before you did this work.
I think we'll have to leave it at that. Okay, let's have the next question, please.
Michael Sinatra, ESNet. I just want to say that just put some little context in on this. Jeff Houston has been routing 2400/12 to various telescope projects that he's been running for many years under the auspices of APAN, and actually at one point I helped him out with some of that too. I was very nervous and I was very concerned about the exact same things Heather was concerned about, so I certainly understand those concerns. I have the same concerns. I would say though, let's not take Manish out to the woodshed. Let's instead go to our RIRs and say, we don't want you issuing these LOAs, because they did, they issued the LOA. So, and they said, you can announce this /12. Go to the RIRs and say, revoke the LOA. We don't want our address space being used in this way.
Another question.
Yeah, Chris Karir's Internet too. So I'm just wondering, how far and wide did you actually advertise the /12s? Because did this affect everyone actually, or just people that had V6 default routes pointed out?
So we did do an analysis on the route views, and our routing announcements were visible for the large majority of route view monitors, as well as in the RIPE region as well. So they did propagate out. The questions?
I think that's everyone. Thank you, Manish.